Linear electric motor. The motor consists of the stator with the three-phase winding and the rotor. The rotor has ferromagnetic part and the conducting layer. Our task is to calculate the currents in the layer, the force acting on the rotor, and the Joule heat losses. There are 6 slots in the stator, but due to model periodicity, we will model only 3 slots. Okay, let's start QuickField now. In QuickField, I create new problem. Motor. Next. Problem type is AC magnetics. Frequency is 50 Hz. Every simulated device is a three-dimensional object. I'm going to simulate only a single cross-section, so the model class is two-dimensional plane parallel. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the model from the AutoCAD DXF file. Here is the file, and I will import it. This is the geometry model. You can simulate it as is, but I'm going to demonstrate you how to utilize the symmetry of the geometry model. So I'm going to reduce the simulation domain. Take a look at this slide again. These vertical lines divide slot face 0 and slot face 180 degrees. Now take a look at this diagram. Conductor 0 and conductor 180 degrees are opposite. To the right from the conductor 0, there is a conductor plus 60. Here it is. And to the right from this conductor, there is a conductor minus 120. Again, this plus 60 and minus 120 are opposite. Next, we have plus 120, and next we have minus 60. Again, they are opposite. That is called odd periodicity. Okay, switch back to QuickField. Here I will switch to insert mode and draw the vertical lines here. And here, let's zoom in and zoom in again. Here. Okay, zoom to fit, switch to select objects mode, and remove the unnecessary parts. This one and these small edges. Now let's assign labels. For labels, we will explain the geometric object's meaning. This one and this one are steel parts. Steel. This is the conducting rail. This is the air. This is slot 0, slot 16, this is slot 120, and this is slot 180. Okay, and I should assign labels to the boundaries. Left and right boundaries make up an odd boundary condition pair. So I will select left and right. Hold the Ctrl button pressed to select multiple objects at the same time. Odd. And this is bottom. And this is top. So far, these are just text labels. Now let's provide physical properties for these labels. Double-click the label name in the tree. The relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of steel is 1000. Steel is laminated, so I do not specify electrical conductivity here, and I do not specify any current density here. Okay. A rail is made of aluminum. Permeability is 1. Electrical conductivity is 37 megasiemens per meter. Rail is not connected to any sources, so the total current in the rail is 0. Well, of course, there will be eddy currents, but the total remains 0. Okay. There is a multi-turn winding in the slots, and each small conductor of the winding carries the same current. So the current density distribution across the slot is uniform. We can model this by specifying the current density value, which is current divided by the conductor cross section. The current is 1844 amperes, and the conductor cross section is, now let me see, I'll click here again. Here it is. (720 millimeters squared), and here I should convert to meters squared, so times 10 to the power of -6. This is the root mean square of the sinusoidal wave. But in quick field you should specify the magnitude. So I will multiply this by square root of 2, and the phase shift is 60 degrees. Okay, I will copy this value and I will use it in other slots. In slot 0, we have the same current density and the phase shift is 0. In the slot 120, the same current density, but the phase shift is 120. And at last the slot 180. Okay. For the periodic boundaries, I specify odd periodic boundary condition. Okay. The magnetic field is contained within steel parts, so at the bottom boundary I specify 0 magnetic potential. Film lines go parallel to this boundary. And at the top boundary again, I will specify 0 magnetic potential. Now the geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Take a look at the results. And here you can see the magnetic field lines and the color map of the current density distribution. I'm going to adjust the field picture and switch from root mean square value to the momentary values. And now I'm going to animate the picture. Here you can see how the magnetic field changed in time. Take a look here at the center. The magnetic field looks like rotating in the counterclockwise direction. Let me adjust the field picture. I will switch on the vectors of the flux density. Now pay attention at this central part, how the vectors are rotating. They are indeed rotating in the counterclockwise direction, so the magnetic field's running to the left. And the force acting on the rail should be pointing to the left. Okay. I will switch the animation off. Now, how to calculate the force? I will use the contour tool. Click to select the rail. Open the integrals. And here is the Maxwell force. Indeed, there is a component pointing to the left, and there is a component pointing down. The stator attracts the rotor. And there are other integrals you can calculate. You can calculate, for example, the total current. Remember, it should be 0. But there are eddy currents, so the Joule heat losses will not be 0. These are the Joule heat losses. They are calculated for the motor of the 1 meter depth. If you have a shorter motor, for example, only 50 millimeters in depth, then the losses will be less. Well, what else you can do here? You can adjust the field picture. I'm going to switch on the color map of the flux density. Okay. You can get the exact values using local values tool. Just click any point. And here you can get the flux density value, the magnetic field strength, and other field parameters. And you can use the contour tool, contour clear, to get the field distribution along the contour line. Use the contour tool, draw the contour line here in the air gap, and open the XY plot. Here is the flux density distribution in the air gap, and usually we are interested in the normal component. And the exact values you can see in the table. Coordinates and flux density components. If you search for the linear electric motor on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.